In this video, I introduce a soft actor-critic and of policy maximum entropy deep reinforcement learning algorithm. Soft actor-critic is an of policy actor-critic deep reinforcement learning algorithm based on the maximum entropy framework. Actor-critic algorithms are based on policy iteration, which optimizes the value function and policy jointly by alternating policy evaluation and policy improvement, as shown here, this actor and this critic. Soft actor critic combines of policy actor critic training with the stochastic actor and further maximizes the entropy of this actor with the entropy maximization objective. Regular reinforcement learning maximizes the expected sum of rewards as shown here. Soft actor-critic uses a more general maximum entropy objective, which favors stochastic policies by augmenting the objective with the expected entropy of the policy over rho pi, as shown here. This term is a soft value of a stochastic policy pi, where alpha is a temperature parameter. The policy evaluation step computes the value of a policy pi according to maximum entropy objective. The soft Q value is computed iteratively. For a fixed policy using a Bellman backup operator T pi, as shown here and explained in this figure, where soft state value function V is given by this equation and explained in this figure. The soft value function for any policy pi is obtained by repeatedly applying T pi. The policy improvement updates the policy using the KL divergence for each state, as shown here and explained in this figure. The two steps are performed until the policy pi converges to optimal policy pi asterisk, such that a Q pi asterisk equal or larger than Q pi. The soft state function V psi, the soft Q function Q theta, and the policy pi phi are parameterized with psi, theta, and phi respectively. The soft value function is modeled by neural networks, and the policy is represented by a Gaussian distribution with a mean and covariance given by neural networks. The soft value function is trained to minimize the squared residual error, as shown here, where D is the distribution of previously sampled states and actions, or a replay buffer. The derivative of GV with respect to psi is estimated with unbiased estimator, as shown here, where the actions are sampled according to the current policy instead of the replay buffer. Soft Q function parameters are trained to minimize the soft Bellman residual, as shown here, where Q theta parrot is represented by a reward and this expectation, where V psi bar is a target value network. The derivative of G and Q with respect to theta is computed by using this formulation, where psi bar is the exponential moving average of the value network width. The policy parameters are learned by minimizing the expected KL divergence, as shown here. A reparameterization trick is applied to minimize G pi, which uses a neural network F phi to transfer state ST to action AT, as shown here, where epsilon t is a noise vector sampled from a fixed distribution, for example, Gaussian distribution. Therefore, the policy objective G pi is rewritten as here. If pi phi is defined implicitly in terms of f phi, the gradient of G pi is approximated by using this equation, where AT is valued at F phi. Soft Actor-Critic uses two Q functions, Q theta 1 and Q theta 2, to mitigate positive bias in the policy improvement step, which are parameterized with theta 1 and theta 2 respectively, as shown here, and trained independently to optimize GQ. One is used to compute the derivative of GQ, and one is used to compute the derivative of G pi. Using two Q functions consisted of the soft Actor-Critic model training. For more details, please check with these references. Thank you. Bye.